All right, so today we're talking about collision theory, and we've kind of already talked about this a little bit. Um, Essentially, we're talking about bonds breaking and bonds forming and the energy that's involved. So you have some background on this already. But specifically, collision theory refers to the fact that when we have particles colliding, so let's say we've got these two particles here that are going to collide and react, there are a couple of things that have to be in place. The first is you have to have enough energy there to break the existing bonds. We already know that that is endothermic. If we're going to break the bonds that are keeping this thing somewhat stable and this thing somewhat stable, that's going to require an input of energy. Okay, so that's step one. The second part is they have to have proper orientation. So if you have a molecule or two molecules, um, there's going to be a specific way that they have to collide so that when they break the old bonds, they can form new ones. So, it doesn't really matter specifically for a given reaction that we understand what the proper orientation is, but it might be that they have to align themselves kind of vertically like this, and therefore if they're aligned like this, they just bounce apart. Okay, no matter how hard they're coming together, they would just bounce apart. Okay, so they have to have enough kinetic energy to break those existing bonds, and they have to be oriented properly. Now, if that happens, we're going to get energy released, as we already know, as new bonds form. Okay, that's an exothermic process, right? Now, specifically, in terms of kind of a little bit of vocabulary here, we have this thing called activation energy. So this is like when we strike a match or spark a fire of any kind. We're providing the activation energy to get those old bonds broken so that we can kind of start a chain reaction, right? What we mean by that is if I have these two molecules that are about to react, if they do collide with enough energy and proper orientation to break their existing bonds, as they form their new bonds, that's going to release energy. And they're probably not the only two molecules in the area as this is happening. They're probably surrounded by other molecules just like them. And by giving off energy to those other molecules, those molecules are going to now start moving faster. And when they collide, they're more likely to react and give off their energy to their neighbors and so forth. So chemical reactions tend to be chain reactions. And so the exothermic part of one set of molecules reacting gives energy for the endothermic part, breaking the old bonds for their neighbors. But that amount of energy that we need just to get everything kicked off is called activation energy. Now, one way to show all of the energetics of a reaction happening is using a potential energy diagram. So this example is for an exothermic reaction. And so what we're looking at on the y-axis is potential energy. On the x-axis is just reaction pathway, or you could say time, reaction progress. There's a couple different ways you could say it. But essentially, here I have my reactants. They, in this case, have relatively high energy, but it's like pushing a boulder over a hill. So overall, that boulder is going to end up down here lower than it started. So that's why we say this reaction is exothermic overall. But there is still this activation energy hill that we have to get that boulder over before it can then go downhill. So if we think about it in terms of bond formation and bond breaking, the uphill is the bond breaking, which is endothermic. That's why it's uphill. We're adding energy. And the downhill is the bond formation, so the formation of the new bonds. Okay, so this would be an example of an exothermic reaction because there's a negative delta H, meaning that we start with an enthalpy that is above where we finished. We're dropping overall. Okay, so but first we have the endothermic part, then we have the exothermic part, and in this case, the exothermic part is much larger, so therefore, overall, we have a net loss of energy, so an exothermic reaction. An endothermic reaction is just going to go the opposite way. So if we look at this very same reaction in reverse, if we wanted to push this boulder back up to its starting place, our activation energy would be huge. We'd have to get all the way back up to the top of this big hill, and then our energy released would be pretty small, right? So the reverse reaction would be just endothermic because the uphill is much bigger than the downhill.